use the divergence theorem to compute the vector surface integral for the given vector field, where n is the outward unit normal vector and our solid region D is bounded by the surfaces x squared plus y squared equals 4, z equals 1, and z is equal to 8 minus y. So let's just begin by reminding ourselves of our divergence theorem here. So we know that the divergence theorem takes the surface integral, the vector surface integral, and converts it to a triple integral over the solid region D of the divergence of our vector field, dv. And so we can even think about this in its computation form, which is the gradient dotted with the vector field f dv. And so looking at what's given here, we see we have everything we need except the bounds on our solid region. So to determine those, I'm going to start by sketching the solid region D in R3. And let's think about what we're given here. We have this x squared plus y squared is equal to 4, which we recognize as a cylinder centered about the z-axis. And then we have two planes. We have z is equal to 1 and z is equal to 8 minus y. So both of these are planes in R3. So as we start to go through the sketch here, what I want to do to get us started, which I think can make sketching in 3 dimensions easier, is to start by thinking about each of these surfaces in 2 dimensions. So marking some of these important points on the z-axis, we want to indicate where z is equal to 1 and where z is equal to 8. So we know that we have a plane at z is equal to 1. And so for now, we'll simply draw a straight line here at z is equal to 1. We also have another plane occurring at z is equal to 8 minus y. And so we'll draw ourselves a diagonal line passing through z is equal to 8 with a negative slope. And then last but not least, we also, this region is enclosed by the cylinder x squared plus y squared equals 4. So you can almost think about that as a rectangle, or adding sides here to this region. So now that we have a general idea of what the shape looks like, we can go ahead and make this look more 3-dimensional. Right, so we want to make sure that we are indicating that this top part is a plane. Again, this is the plane defined by z is equal to 8 minus y, with the cylinder on the side here. So let's start with the bottom. We have another plane on the bottom defined by where z is equal to 1. And then we also have our cylinder. So now we can really appreciate our 3-dimensional region D, and we can even think about the projection that it's casting, or the shadow that it's casting, into R2. So this green region here, below that is our 2-dimensional region R. And so we want to use this sketch now to define the bounds on D. So we can see just in looking at this graph that z is going to be greater than or equal to 1, less than or equal to 8 minus y. And without having to do any further calculations, if we think about the solid's projection again into the xy plane down here, we can see that it's creating a full circle. And based off of our cylinder, we know that that circle has a radius of 2, since 4 is equivalent to 2 squared. Actually, it may, in retrospect, be helpful to think about our two-dimensional region here. If you see it, by all means, go for it. Otherwise, when you sketch the two-dimensional region, or the projection of the solid into R2, we realize, hey, this is a circle. It's probably going to be more convenient to integrate with respect to polar coordinates. So we can say that our radius is greater than or equal to 0, less than or equal to 2. And since it is a full circle, we know that theta is going to be greater than or equal to 0, less than or equal to 2 pi. And then looking back at our z bounds here, we want to rewrite y using our polar coordinate conversion formula. So this is going to be 8 minus r sine of theta. So these are the bounds of our solid region D. So with these bounds, the only thing remaining to find is the divergence of the vector field before we integrate. And again, we'll recall that the divergence of our vector field is equal to the dot product of the gradient and the vector field. So it is the sum of the partial derivative of f with respect to x, partial derivative of g with respect to y, plus the partial derivative of h with respect to z. So keeping in mind that our given vector field is defined by the components f, g, and h, we'll go ahead now and we'll find our partial derivatives. So the f component is defined as y squared z. The g component is defined as 2y minus the natural exponential raised to the z. And the h component is defined as sine of x. So we have the partial derivative of f with respect to x is 0. The partial derivative of g with respect to y is 2. And the partial derivative of h with respect to z is 0. So therefore, the divergence of our vector field is 0 plus 2 plus 0, or just 2. And we're ready now to go ahead and evaluate the surface integral using the divergence theorem. So by the divergence theorem, we are taking our surface integral over S of the vector field dotted with the normal vector ds and converting this to the triple integral over the solid region D of the divergence of the vector field dv. So this is going to be the integral from 0 to 2 pi, the integral from 0 to 2, the integral from 1 to 8 minus r sine of theta. We found the divergence to be 2, and then since we're using cylindrical coordinates here, we have the differential r dz dr d theta. And we're ready to start evaluating. So this is equal to the integral from 0 to 2 pi, the integral from 0 to 2 of 2r z from 1 to 8 minus r sine of theta. And that's dr d theta is still on the outside here. So in evaluating, we have the integral from 0 to 2 pi, the integral from 0 to 2 of 2r multiplied by 8 minus r sine of theta minus 1. And then don't forget your dr d theta on the outside. So let's see, we can simplify this. We'll have 7 minus r sine of theta. And before we can integrate again, we want to be sure to distribute that 2r through to both terms. So we're left with the integral from 0 to 2 pi, the integral from 0 to 2 of 14 times the radius minus 2 times the radius squared sine of theta dr d theta. So now we're integrating with respect to the radius r. So this is the integral from 0 to 2 pi of 7r squared minus 2/3 r cubed sine of theta from 0 to 2 d theta. So we have the integral from 0 to 2 pi of 7 multiplied by 2 squared, which is 4, minus 2/3 multiplied by 2 cubed, which gives us 8, sine of theta. And then fortunately, when we substitute 0 in here, we are left with just 0. And we are so close now. This simplifies to the integral 0 to 2 pi of 28 minus 16/3 sine of theta d theta. And so integrating now with respect to theta, this is 28 theta minus a minus cosine, so plus 16/3 cosine of theta from 0 to 2 pi. So we have 28 multiplied by 2 pi plus 16/3 cosine of 2 pi. And then we're subtracting when we substitute 0 in. 28 times 0 just disappears. Plus 16/3 cosine of 0. And so we know that cosine of 2 pi goes to 1. Cosine of 0 goes to 1. Leaving us with 56 pi plus 16/3 minus 16/3. So those two last terms cancel each other out, leaving us with a beautiful final answer of 56 pi.